You start. Good morning, ladies and gentlemen, and welcome to today's seminar, Mechanical Engineering Department seminar, Thor, the Lifesaver. Is going to be presented by Dr. Ajay Kothari. He is the president and founder of Airstock Corporation, which is an aerospace R&D company located in College Park, just suburban of Washington, D.C. Dr. Kothari got his bachelor's from the University of Bombay and his PhD and master's in aerospace engineering from the University of Maryland, College Park, Maryland. He has over 45 publications, and he was awarded National Merit Scholarship. He's been invited to speak on aerospace subjects by many entities, and he's been interviewed on television shows a number of times. His articles on space-related activities have been published by various newspapers. He's a member of the Screen Actors Guild, and he's also an artist. So, Dr. Kothari.
Thank you very much, Dr. Gupta, Ashwani. And thank you also for the Clark School, to the Clark School of Engineering for inviting me here today. In particular, I want to thank Dr. Samuel Graham, the Dean of Engineering here, and also the head of the Department of Mechanical Engineering, Dr. Balachandran, and the head of the Department of Aerospace Engineering, Dr. Alison Flatow. And of course, my thanks also to Professor Gupta for arranging this and inviting me here. So this particular talk is something that I kind of discovered or ran into recently and was very excited. It's kind of an amazing thing. It's about thorium. Thor, of course, you know, Thor is the Norse god of thunder and lightning and other aspects of, and also good things. So the thorium, which is an element on the periodic table, of course, obviously, is a fertile material, not a fissionable material, and so element. And so then that makes it possible for us to take advantage of it, especially since it's in tremendous abundance here on Earth and also in the United States. So with that, I thought that maybe I'll look into this and transmit whatever ideas that I have developed on this. And not only just for terrestrial use, but as you can see here, I have included here Starship, so for the space use, and the Falcon Heavy of SpaceX, of course we all know, and also New Glenn's upper stage and the booster stage, etc. This is what effectively it looks like, the whole plant. So it has terrestrial use, and this talk is about terrestrial use, but also about space, its use for space. So let's start with the second slide here. So what does it look like? What does thorium look like? It looks like this as it comes out of the mines, and it's a byproduct of digging out monazite mines, digging out things from monazite mines. And so it's just, basically it's just thrown back because it's, you know, not used at this point in time. This is what the pellets look like. And look at this. We have enough reserve of thorium here, 6.3 million ton, and 1 ton is of course 1,000 kilograms. So we have that much thorium, and that much thorium in terms of energy, and I'll talk about why, is equivalent to, you can see here, it's equivalent to 5 million barrels of oil. 1 ton of thorium is roughly equivalent to 5 million barrels of thorium. So if you multiply those two numbers, we have about 30 trillion barrel worth of thorium on Earth. And we have an actual oil, which is 1.8 trillion. So it's just amazing, amazing amount of energy which is available here. This is what the thorium plant would look like when it is built, and I hope it is built soon. This is the reactor here, part here, and on the left. And there is a freeze valve here at the bottom. That helps, and I'll talk about that when we come to it. There is a heat exchanger here, another heat exchanger, and a turbine that produces electricity. Now, what has been covered recently about this thorium, and it is, as you can see here, in an article that was published very, very recently, the global nuclear power is ready for a comeback. And the reason for that is that we have, all these, all the requirements, and the requirements are the countries are realizing that they can meet their climate, energy, and national security goals without, just with these, the terrestrial solar and wind. Just it's not possible to do that. And so we need something else. We need something like this thorium. And this is an amazing add-on to anything else that we want to do. Not only add-on, but I mean, it could be a major factor in the amount of energy that we can produce this way. So let's go to the next slide. Another article that was published here. This is also quite interesting and quite amazing. That the nuclear power here offers more energy in less physical space than solar and wind, and yields more energy per pound than some fossil fuels, which is amazing. That the fossil fuels or solar farms or wind farms, they require a lot more physical space compared to this nuclear energy, especially this nuclear idea. This is a new nuclear idea, which is now a generation 4, actually. And so this is molten salt reactor idea is just absolutely amazing. So the idea is that the writer, the author of this, says that this is one of the nuclear uranium-233 is the nuclear super fuel that we are not using. Why we are not using is beyond me. This is just absolutely amazing that we can do this. We can go to uranium-233, which is bred from thorium and resist use in nuclear weapons. Results with reaction from thorium, plentiful, as I showed, ubiquitous element currently. It's just, we have lots and lots of thorium available, and the amount of energy that it can produce is 200 MeV per atom. So it is just absolutely amazing. So the possible advantages, what are the possible advantages of going this molten salt thorium way? The thorium is abundant, as I said, 3 to 4 times more abundant than mined uranium, which consists of uranium, which is consists of 0.7% uranium-235, which is the fissionable element, and the rest is uranium-238, which is not fissionable as available. So only only U-235 is fissionable when you actually multiply that by the 3 to 4 times more abundant total than total uranium. It really becomes about 400 to 500 times more abundant than the fissionable uranium-230, 235. And so, since most of it or all of the thorium can be converted into uranium-233, in terms of fissionable element, that ratio is almost 4 to 500. Thorium is fertile but not fissionable, so it is not radioactive to touch. It goes without saying that the CO2 emission, there's no CO2 emission, so CO2 sequestration is also not necessary. And the fourth point, the pollution, for example, in countries like India, is just awful. It's just too much. And such a technology would go a long way to saving millions of lives. If we don't do it, it really is shameful for us to not avail these people of this kind of technology and having to rely on coal and other things instead. The thing about this is that unlike the light water reactors or pressurized water reactors, light water or heavy water reactors, this one does not require high pressure. That light water reactor or PWRs, pressurized water reactors, require high pressure because the coolant there and the moderator is water or heavy water. And obviously, to keep it from boiling into steam, boiling away and as steam, you have to create very high pressure of 150 to 200 or so atmosphere. You don't need to do that here. So it cannot blow up. It cannot explode the way that, the Fukushima exploded or Chernobyl exploded, or even Three Mile Island had issues about that. That cannot happen here. The other huge positive above comes with one negative, which is the temperature of the liquid salt now is much higher, 600 to 700 degrees centigrade. And so that obviously has a corrosive impact on containment vessels, and we have to figure that out. Universities have to play a big part in trying to figure that out, and I hope that we do that. But at the same time, this higher temperature also makes it possible to create steam at very high temperature, and the electricity conversion through turbine is at a much higher efficiency, almost 45%, which is about twice as much as LWRs. And then I showed you the freeze valve below earlier. That freeze valve, that's another thing, which is that if the temperature of the molten salt becomes too hot, then the freeze valve will melt and the entire molten salt will drop down underground into the containment tanks that we have down there. And so there is a fail-safe mechanism also available. There is also an internal fail-safe, which is that as it gets hotter, the distance between the nuclei increases, and so then the chance of fission also decreases. And so there is that also. So there are two possible scenarios here. The lack of high pressure that, as you can see, you have seen, the nuclear reactors of today, of generation 1 and 2, and maybe even 3, are huge. They have dome, very thick concrete dome, and that has to obviously contain all that pressure. Now we don't have that. And if we don't have that, the size of the entire nuclear power plant also decreases. And so when the size decreases, the mass decreases. And so then it's possible to apply that, use that for smaller physical space and also for space applications. About 90 to 99% of the thorium fuel is burned. So the byproduct or waste products are almost non-existent comparatively compared to what we have today, the solid fuel reactors, the thermal reactors. And then let's go to the next slide. And so the molten salt is in exactly the chemical medium amenable to partitioning, and the liquid fuel is continuously mixed and homogenized as it circulates. And so in this case, we don't even have to shut down the power plant to add, like what we have to do now, is that you have to shut down the power plant to put new rods in there. You don't have to do that with this. It's continuously being fed. There are possible disadvantages, however, and those are material buckling. The half-life of protactinium, which I'll discuss how it's produced, is about 27 days. And so during that time, while it is decaying, beta decaying into thorium-233, it's possible for it to also absorb neutrons. And when it does so, it can produce some material, some elements which are not desirable. And so what we need to do is to, once that process starts, protactinium, is being produced, the uranium-233s is being produced, and they more or less equate after a certain time. And so no more uranium-233 can be produced. And so that's a problem. And so this protactinium and uranium-233 need to be separated, and that can be done rather easily, so to speak. It is again something that universities can get involved in, and that's a chemical processing plant which is in the loop, because protactinium tetrafluoride is, as you can see here, the separation is very easy. It can be chemical processed. Because protactinium tetrafluoride is liquid, whereas uranium hexafluoride is gaseous. So they'll be separated in a plant, in a gaseous plant, like I had shown you before. Here on the left-hand side, you can see here a chemical processing plant, which is what does that work. So let's go back to the big possible disadvantage, of course, is that the research in thorium is not being done. And why it is not being done, I don't know. I'm just completely shocked. It should be done. It should be done by the government. It should be funded by Department of Energy at whatever level that can be. All right. So now, why not the for the nuclear? Why not the liquid water reactors or the LWRs or PWRs, pressurized water reactors, for water or heavy water? So why not those? They operate, of course, at extreme pressure, as I discussed before. They also operate at low temperature, which is about 350 C, and that 350 C is just gives you conversion efficiency of about 25-35%, and so that's a negative. And it uses solid fuel technology, resulting in less than 5% nuclear fuel utilization, and produces large quantities of plutonium, which is creating proliferation. There is no plutonium produced with this thorium power plant, no plutonium. So that particular type of proliferation concern is gone also. So it's an economically viable system without massive subsidies. True costs are hidden from public. So this was a screenshot from a presentation given by Jim Kennedy. Then I wanted to do an actual calculation about the energy, etc. So here, 1,000 ton of thorium, 1,000 kilogram of thorium, 1 ton of thorium is equivalent to 1,000 divided by 0.232 or 0.2, creating 2 gram mole of thorium. So this is that many 4310 gram moles of thorium is what is produced. Now, if we multiply that by Avogadro's number, and then the amount of energy which is produced per atom, and the conversion to joules instead of MeV, you get something like 8.322 e to the 16 joules per ton of thorium. That is for 1 year. Let's say 1 ton of thorium used for 1 year would give you 2.6 gigawatt year of electricity. And the most of this, so basically using 1,000 ton of thorium per year, 1,000 kilogram of thorium, 1 ton of thorium per year is all you need to have a 2.6 gigawatt thermal power plant that runs, continuously per year. So that's all you need per year, 1 ton per year for that power plant. The world's electrical need is about 55 10 to the 9 gigajoules per year. This means 667 ton of thorium can fulfill this need entirely for the whole world. And 667, as we saw, that total that we have in the world is 6 million ton of. So you divide 6 million by, say, 1,000 ton of thorium. Let's say that the conversion, considering the efficiency of energy conversion from thermal to electric, that's about a factor of 2 to 3, this number. So with this 6.3 million ton of reserve, we have enough thorium to last 5,000 to 6,000 years in this world. And in this country, with a higher energy requirement per person, we have enough thorium to last 600 years. I'm sure that by that time, we'll have licked the fusion problem and solved this. So this is a fantastic placeholder or a filler from now until that happens, say 100 years from now, 50 years from now, 200 years from now, whenever that happens. It's an absolute must for us. Okay, so how does this happen? Why does this happen? That happens because of the reason why the protons and neutrons together are being held together in nucleus when all protons have positive charge and they repel each other. And so one has to have some kind of a glue there. And so that glue is provided by the neutrons through the strong nuclear force. That's the theory. And so anything other than a certain number of proton and neutron, when you have that, the radioactivity is not emitted. But if you are out of that particular balance, that's when an element becomes radioactive. So that's what is happening here. The strong nuclear force that we have here, which is holding the neutrons and protons together, which is holding the neutrons and protons together. And so obviously that becomes then the binding energy for the nucleus. And that energy is an incredible amount. And that energy, well, then one of these forces physicists have been talking about is the strong nuclear force that I talked about. That energy that is released is 200.1 MeV of energy released per atom of uranium-233 upon fissioning. This energy is 1,000,000 times greater per unit mass than chemical, such as that produced by burning fossil fuel. And 1 kilogram of uranium-235 or thorium-232 converted to uranium-233 via nuclear process releases approximately 3,000,000 times more energy per kilogram of coal burned conventional. Coal, we can get rid of coal mines, get rid of coal burning, and this is just so much more energy that can be produced that it'll solve all our problems, actually. Climate problem, CO2 problem, energy deficiency problem, all of them can be solved with this particular idea. How does this happen? So you have a thorium atom here. That thorium atom is obviously atomic number is 90 and atomic weight is 232. That when it is one more neutron is inserted into that nucleus, it becomes thorium-233, does not change the atomic number, obviously. Then that thorium-233 decays very fast in about 22 minutes into protactinium, which is also the same atomic weight, which is 233. And then that particular protactinium over 27 days, does another negative beta decay, and that becomes uranium-233. So obviously the beta decay changes the atomic number to 92 now after 2 beta decays. And so that then becomes, this one becomes fissionable. It fissions, it divides into 2 daughter products, which are xenon and strontium, and produces extra neutrons for chain reaction. That particular then reaction or division into daughter products releases 200.1 MeV of energy per atom, and you multiply that by Avogadro's number, which is a huge number, 10 to the 23. You can see that it will produce tremendous amount of energy. So this is more or less the same. How does it work? The thorium atom changes into protactinium, and protactinium into uranium, and then the fission occurs. So the daughter products are xenon and strontium. Xenon is 54 atomic number, and strontium is 38. Together is 92, as you can see. So that's what happened here. Now, not only does this strontium and xenon produced have not very long half-life like the uranium products do, uranium-235 products do. It's more like thousands of years instead of hundreds of thousands or millions of years. So it can be stored much more easily. But 1% of the product is also technetium, and that technetium can be used for technetium and other transuranic elements that can be used for medical diagnostics that we need. And so that particular medical diagnostics here worldwide use you can see here is, is quite a bit. Here. So this is the worldwide use of radiopharmaceutical use of technetium. And in this case, um, of the medical procedures using technetium, we have myocardial perfusion and other several different things which are being done diagnostics with. And this is a screenshot from presentation by Kurt Sorensen of Flight Energy. So most of this waste is useful for radiopharma diagnostics and medical industry. That which cannot be has half-life of hundreds to thousands of years, as opposed to uranium-235, which is hundreds of thousands. So, which I mentioned before. Okay, now this is what the thorium uranium-233 plant that was molten salt reactor that was actually built in the 60s looked like. Look at the size of this. This is the rods which are going in, graphite rods which are going in, and this is the total size of the reactor. This is a 2 megawatt reactor. It's a small size, and if you look at that, and this thing ran for about 6 years, 5 years, from 65 to 69, and it was at Oak Ridge National Lab of designed by Dr. Weinberg. As is seen, this is just a power plant. The heat exchangers and turbines will be larger, but even then, the power generation part is much, much smaller than what we have currently. It's a win-win-win-win-win. It's amazing. This is a 2 megawatt reactor, basically. A 1 gigawatt reactor will be about 500 times bigger, or about 8 times larger in each dimension. 500, cube root of 500. With this 2 megawatt plant at about 1 meter in each dimension, the 1 gigawatt reactor will be 8 by 8 by 8, much smaller than PWRs of today. So another positive plus. China is doing this already. They have already built some, and the reactors have the molten salt reactor with uranium to thorium have been built in Wubi province in China. We don't know. They have started their experiments in September, October of last year, almost a year ago. We do not know what the results of that are. They are not released. Norway is doing some work in this thorium also as another country. And of course, we know that many other countries like China, India, and Netherlands are also very, very much working on this. There might be other countries also working on it. So for Earth, as you can see here, for humanity of Earth, this solution is available today with enough supply of thorium to last us thousands of years, and with zero CO2 emissions and zero pollution. We do not need to build tens of thousands. This is one of the possible solutions that have been offered, but that's kind of a ridiculous solution to build 50 tens of thousands of 1 gigawatt space-based solar power SBSP or SSP plants at geostationary orbit and associated rectina on Earth. This is a infinitely better solution than that. This solution needs to be developed right here in America. The time is now for us and for the rest of the pollution-ridden countries to be aware of this technological marvel. One hope that this administration will pay attention to it and find a reasonable path for us soon. And also the same technology that would be developed here for Earth can also be combined for cislunar space, for moon, and used for Mars, combined and used for Mars. I mean, synergized for those possibilities also. So let's move to that now. We know that on the moon, thorium has been found by Chang'e 2. As we discussed before, 1 kilogram of thorium taken from Earth to begin with can provide 2.6 thermal megawatt plant per year. That's a pretty large plant for a habitation module or some other equipment that requires heat and energy and electricity. Imagine 10 such plants in 10 different locations with 10 kilograms of thorium taken from Earth and the associated salt, which will eventually become self-sustaining with lunar thorium. Only the first such plant will require neutron-producing radioactive material to commence the chain reaction. The uranium-233 thus produced can provide any further neutrons for additional reactors, thus becoming self-sustaining. For power on lunar surface, however, this is one of the most promising solution actually, but there are some other solutions which should be combined together to do that. So how do we do the nuclear propulsion with this? So we know that the best chemical plant that we have or engine we have, SSME, for example, gives you about 453 seconds of ISP. And at the most for vacuum, it can give you, designed for vacuum, it can get up to 462 seconds. But the nuclear, like NERVA project, came up with a number like almost 880 seconds of ISP, 870 seconds of ISP. If you use the molten salt reactor instead of what we have in NERVA, which is a solid pellets, hydrogen going over the pellets, we will have at least 665 seconds of ISP. Now, obviously, that's not as high as NERVA, but NERVA was extremely heavy. In this case, if we consider a considerable reduction in size and weight compared to NERVA type solution, MSR may be more attractive at system level. And combine everything together and fly this rocket at system level. That's what can happen. So and this is how you do it. This particular rocket is the upper stage of New Glenn, which was designed by Astros Corporation with our code space side as a simulation that you can see here. Is the hydrogen tank and the oxygen tank in what it was designed. Instead of the oxygen tank, if we were to put the molten salt reactor there and fly the oncoming hydrogen from this hydrogen tank over it at these high temperatures, about 1200 degrees centigrade or hopefully higher even, then the heated ongoing hydrogen that comes out will give you 665 seconds of ISP. This can be done. Then, not only that, but and of course, in this case, this is the oxygen tank instead will become the T-MSR. And then, in this case, we will have to place the hydrogen tank, of course, farther away, much farther away from the high temperature reactor. But that can all be done. We are not carrying oxygen anymore in this case. This is good for second stage. Then, once you get to the moon or Mars, you can do what is called reuse or repurposing of the the molten salt reactor part. The molten salt reactor part remains, and that is then transfer that to a turbine in this case, like before, like terrestrial use, a closed loop CO2 or some other gas turbine that produces electricity. In this case, you don't have to run them at high temperature of 1200 C, 700 C is enough, and it will create a good amount of electricity that way, closed loop CO2. Or you can use it for thermal plant and to regulate the ice melting, etc. So this is a really good use of this in terms of repurposing also. So finally, I would say that for United States and world terrestrially, in summary, to summarize, thorium offers immense supply of energy that can last several thousand years. No CO2 emissions or pollutants, no high pressure explosion possibility, twice the efficiency of conversion to electricity as current PWRs, natural and fail-safe freeze valve mechanism for if something goes wrong, which I talked about. Less than 1% radioactive waste product compared to 95% for PWRs of today. No plutonium can be used, is produced that can be used for nuclear explosions. It does not need to be near water supply, like what we have now. Everything has to be, all of these plants have to be near river, lake, ocean, or something. This one does not. And so it can be built even in desert. And so it's ideal for moon, Mars. It can be built anywhere in this country, anywhere. It can be built in Sahara Desert. Can be fueled continuously with chemical processing in the loop without having to shut down as in PWRs. Amazing. There is nothing more that can be offered by other solutions. What more can be there? This is an incredible solution. So I respectfully urge this administration to take this idea seriously, and provide some funding for research and development and engineering for this. As far as the you gentlemen and ladies are concerned, for the University of Maryland, a few suggestions here. For mechanical engineering, for example, here, Dr. Gupta and other people do computational analysis to assess the heat transfer in heat exchangers, build a 30 centimeter dimension 3D printed simulation, no reactor for now, to confirm the containment pipes and heat exchangers can work efficiently and last for many months. Containment end pipes can be made from seasick material, being now suggested for use in hypersonic flights. For the aerospace engineering department, obviously there is a lot that can be done. The application for cislunar and for moon Mars travel are promising, which can be analyzed by students through research topics for master's PhD. Topics based on repurposing of nuclear T-MSR rocket for energy on moon and Mars can be explored and papers published. Very interesting topics and very interesting MS PhD topics also at the same time. Now, it is possible to fly a vehicle on Mars, because Mars obviously has some atmosphere, using the heat generated through T-MSR at turbine-powered subsonic speeds with no combustible fuel needed. 10 grams of thorium fuel, or whatever you call it, or U-233 is enough, creates enough energy for air to be compressed and expanded through the nozzle, creating thrust for that vehicle to fly around Mars for an entire orbit. 10 grams. 10 grams. If you take that from here, I mean, I don't know. No, we know that there is thorium on Moon. I don't know about Mars, but whether there is some or not, taking, few kilograms of thorium to Mars is not a big deal at all. And that can really provide the vehicle for Martian colonies to future experimentation, mapping, and transport. So Thorium-MSR solution is going to go big worldwide and certainly in US. So in my honest opinion, respectfully submit or request the Clark School to revive the nuclear engineering department, partly concentrated on this TMSR. So with that, I'm concluding this talk with this painting that I made about first woman going to Mars and going there in a very gingerly fashion without disturbing any topology of Mars, geography of Mars. As you can see here, it just blends in everywhere. And this is what we are aiming for and hoping for. And we need to all work together to make this happen. We need to work together to make the energy deficit go away for the rest of the world and for us, of course, obviously. And so here is a solution that can do that. Let's do it. Let's work together. Thank you.